Hi, welcome to this lecture on the union-find data structure. Here's the outline for the lecture. We'll first talk about the dynamic connectivity problem, and then we will discuss the API for a data structure called the union-find data structure that you can use to solve the dynamic connectivity problem. And then we will discuss three implementations of the union-find API. The first implementation is called quick find. The second is called the quick union, and the third is called the weighted quick union implementation. And then finally we will discuss the performance characteristics of the three implementations of the union-find API. So let's first start with the dynamic connectivity problem. Consider an input sequence of pairs of integers where each integer represents an object of some type. Okay? And the pair PQ means that P is connected to Q. So for example, here you have 10 objects which are labeled 0 through 9, and then for input you receive these pairs of integers, right? Now when you receive a pair such as 4, 3, what you want to do is you want to connect the points 4 and 3 if it's not already connected. Okay. Now the connection may be direct or indirect. All right. So the first pair that we get is 4, 3. So you need to first figure out if 4 is connected to 3 or not. And in this case, 4 and 3 are not connected. So you need to establish a link between 4 and 3, which is what you see here. And then comes the pair 3, 8. Here again, you check if 3 and 8 are connected or not. Well, they are not connected. So you establish a link. Okay. And then comes the pair 6, 5. 6 and 5 are not connected yet, so you connect the two. And then comes 9, 4. 9 and 4 are not connected, so you establish a link between the two. And then comes 2, 1. 2 and 1 are not connected, so you establish a link between the two. And then comes the pair 8, 9. Right? Now, 8 and 9, these two points, they are not directly connected. However, there is a link from 8 to 9. There is an indirect connection between 8 and 9. So what we do is we don't establish a direct link between 8 and 9 because they're already connected, although indirectly, and that's okay. So that's why this pair is in gray, right? Meaning we are not establishing a direct link between the two. And then we process the pair 5, 0. 5 and 0 are not connected, so you establish a link. Then comes 7 and 2, they are not connected yet, so you establish a link. Then comes 6, 1, they are not connected, so you have a link there. And then comes 1, 0, but 1, 0, though not directly connected, there is a link from 1 to 0, an indirect link, right? So you need not establish a direct link between 1 and 0. So 1, 0 is in gray. And then the last pair is 6, 7. So here again, there is no direct link between 6 and 7, but there is an indirect one. So we don't establish a direct link, right? So 6, 7 is also in gray, and we are done processing all the pairs. Okay. So the goal of the dynamic connectivity problem then is to devise a data structure that will help us decide whether or not a new pair of objects is connected. Okay. And if they're not connected, the data structure would provide a mechanism for establishing a connection between them. And we want to solve this efficiently. So we want to be able to figure out if 2 points are connected or not efficiently. And if they're not connected, we want to efficiently connect the 2 points. Okay? Now there are many applications of the dynamic connectivity problem. So for example, you can use this idea to determine if 2 vertices in a network are connected or not. Right? And then you can determine if 2 variable names in a computer program are equivalent, meaning they refer to the same object. Right? And then finally, if we think of the integers as belonging to mathematical sets, then when we process a pair such as PQ, we are asking whether they belong to the same set or not. And if they don't belong to the same set, then what we do is we unite P's set with Q's set, putting both in the same set. Okay? So that's another application from set theory. where you make use of the dynamic connectivity problem. Right? Okay, now some terminology before we continue. We're going to refer to the objects as sites. So those dots that you saw in the previous slide, we're going to call them as slides. And then the pairs are going to be called connections. Okay? And then finally, the groups of connected sites are going to be called components. Okay? So if a collection of points is connected, meaning if you can get from one point to another directly or indirectly, then what we have is a component, right? So within a component, you can get from any point to any other point, from any site to any other site, right? But if you have two sites that are in different components, you cannot get from one to another. Okay? So we have the notion of sites, and then we have connections between sites, and then finally we have these islands or connected components. Okay, and we are going to assume that we have n sites in total, capital N sites, and these are going to be given names which are simply integers running from 0 through n minus 1. So the labels associated with the sites are going to be numbers from 0 through n minus 1. And we can solve the dynamic connectivity problem using what is called the union find data structure. So it's the union find data structure that will help us answer a few questions efficiently, such as whether two objects are connected or not, and with the union find data structure we can also establish a connection between those two sites if they're not connected yet. Here's the API for the union find data structure. So UF is just a short form for union find, right? Okay, so let's go through the API. So the first entry is of course the constructor, and the constructor takes an argument n, the number of sites, okay? And it initializes an empty union find data structure with those many sites, with capital N sites. And then once you have a union find object, then what you can do is any of these things. So find is an instance method that takes a site ID as an argument. Okay, so P is a site ID, and what it returns is the component identifier, meaning an identifier associated with the component to which P belongs to. Okay? And the component identifier is basically going to be a number from 0 through n minus 1, right? So each island or each component will be given a number, okay? And it's the component number for the site P that is returned by the find method. And then the count method simply returns the number of components or the number of islands. And then connected takes two arguments, two site IDs P and Q, and it checks if those two sites are connected or not. Okay, and it returns true if they are connected and false if they are not connected. In other words, it returns true when the two sites P and Q belong to the same component, and false otherwise. And then finally, the union method takes two sites as arguments, or the IDs of two sites as arguments, and it establishes a connection between them. Okay, so it's the union method that you use to connect two sites. So that's the API. What we're going to do next is look at a very simple client of the union find API, and that's what is shown here. So this program is called UF client, and all that it has is a main method. So let's go through the main method. So the first thing that we do here is receive an integer from standard input that denotes the number of sites that we want to process, which we store in this variable capital N. And then we build an object of type union find, and the particular implementation that we're using here is called the quick find UF, and we'll talk about this in a bit. Okay? So that's just one particular implementation of the union find API. Alright, so we build a union find data structure with n sites, and then inside of a while loop we receive pairs of integers such as what is shown here. Right? So as long as stdin is not empty, we receive a pair P and Q from standard input, and then we make use of the connected method from the union find API to check if P and Q are connected or not. And if they are already connected, then we simply continue to receive the next pair. So we don't do anything in that case because P and Q are already connected. But if P and Q are not connected, then we make a call to the union method from the union find API to connect the two sides P and Q. Right? And we print the fact that we established a connection between P and Q. Okay, so for any pair where we establish a connection, we simply print the pair out. All right, so we keep doing this for all the pairs of input, and then once we are done, at the end we simply report the number of components by making a call to the count method from the union find data type. Right? We simply report the number of islands that we are left with. Okay, so now let's look at some input and output. So the input is stored in a file called tinyuf.txt, and this input is precisely what you see here. So the first number 10 denotes the number of sites, so that's capital N, and then you have these pairs of numbers. So 4, 3 is this pair, 3, 8 is the second pair, 6, 5 is the third pair, and so on and so on, and 6, 7 here is the last pair of input. Okay? And what we're going to do now is run the UF client, giving it this file via standard in. That's what is done here, and the program comes back with this output. So it's printing out these pairs because for each of these pairs a connection was established, and the pairs that don't show up here were already connected, so we don't establish a connection. So for example 4, 3, 3, 8 and so on are these guys, and this pair here 8, 9, for which we didn't establish a connection, doesn't show up in this list, right? And then finally the program prints the fact that there are two components after all the input pairs are processed, and that's correct. This is one component or island, and this is the other component or island. All right? Okay, so that's a very simple a client of the union find data structure. Now what we're going to do is talk about different implementations of the union find API, and we're going to start with the implementation that's called quick find UF. Okay, so let's go through it. So the two instance variables that we use in quick find UF are an integer array called ID and an integer called count. Now ID is going to be an array of size capital N, where N is the number of sites. All right, and each element in ID is simply going to store the component identifier of the corresponding site. So ID is simply an array that goes 0, 1 and so on all the way up to n-1, and what it stores for value is the component identifier. Okay, it's the ID of the component to which this site belongs, component ID of 0. Similarly, this number here is the component ID of the site n-1 and so on. Okay, so the value that corresponds to an index I in the array ID is simply the component identifier of the site I. Right, so that's how you want to look at this array. And then count is going to simply store the number of components. Right? Okay, so now let's look at the constructor. So in the constructor, what we do is we first initialize the ID array. So we create it with size capital N, and when we do that, all the values are going to be initialized to 0, okay, because it's an array of primitive ints. And then we set the instance variable count to N. Okay, so what we are saying is that initially, when we have not processed any pairs of input, initially the number of islands or components is precisely N, because every site is a component or an island in itself. Okay, and then we initialize this array ID as follows. So I goes from 0 all the way up to n, and we say that the component identifier of the site I is simply I. All right, and this makes sense because initially we haven't processed any of the pairs, so each site is its own component. So 0 has the component ID 0, 1 has the component ID 1, 2 has the component ID 2, and so on and so on, and n minus 1 has the component ID n minus 1. Okay, so that's what is achieved by this initialization. So once the for loop is done, every site has the site ID for the component ID. Okay, so that's the constructor. Now, what is the running time of the constructor? Well, because of this for loop, it is order n. Okay, so it's linear. Okay, so now let's talk about the find method. Well, the find method is extremely simple. You're given a site ID and we want to return the component identifier of that site. Well, we simply look at the ID array at that index p and return the corresponding value. Okay, because ID of p is the component identifier of the site p. Okay, what's the running time of this method? It's 1 because it's simply an array index. Okay, what about count? Well, count is very simple. You simply return the value of the variable count because that keeps track of the number of components. And that's in the order of growth, or the running time there is also 1. The next method is called connected, and that receives two site IDs as arguments, p and q, and we want to return true if p and q are connected. But what does it mean for p and q to be connected? Well, they have to have the same component ID, right? That's what we check. So we return this Boolean expression that says ID of p equals ID of q. So if this Boolean expression is true, then it means that p and q have the same component identifier, right? Meaning they're in the same island. But if this expression is false, it would mean that p and q are in different components or different islands. Okay, so that's connected. What's the running time here? Well, it's also constant because we are simply indexing an array. All right, so that's a constant time operation. And then finally we have the union method from the API. How is that implemented? Well, we receive two site IDs as arguments, p and q, and what we do is we get their component identifiers, okay, by simply looking at the array at indices p and q. So the component identifier of p is PID and the component identifier of q is QID. And then we check if they are the same. If so, we simply return because there is nothing to be done, because this would mean that p and q are connected, right? So there is no need to establish a connection between the two. But if they are not connected, what we do is this for loop where I goes from 0 all the way up to id.length. Okay, and then whenever we find ID of I equals PID, so we are basically looking for the value PID in that array. Okay, and wherever we see the value PID, we simply replace it with QID. Okay, and this has the effect of connecting p and q. So we scan the array. So we simply scan the array, and wherever we see the value PID, we simply replace it with the value QID. Okay, so that's what we do. And since we are connecting the sites p and q, the number of components goes down by 1. Right, so each call to union, if it does establish a connection between p and q, reduces the number of components by 1, which is why we do count minus minus. Okay, so that's it. So that's the first implementation of the union find API called quick find UF. And what's the running time of this method? Well, this for loop, it is linear because it goes all the way from 0 to the length of the ID array, which is capital N. Okay, so the running time of the union method is n. All right. and that is when you actually make a connection, right? So if you end up connecting P and Q, the running time of the method is, in the worst case, is n, right? So now let's look at a trace of calls to the union method, all right? From the quick find UF implementation. So here, what you see is the ID array, right? So initially, the values in the ID array is simply the site ID. So 0 corresponds to 0, 1 to 1, 2 to 2, 3 to 3, and so on, all the way up to 9 corresponding to 9. Because initially, when no input is processed, the component identifier of a site is the site ID itself. And then we get the pair 4, 3, all right? So at this stage, what is the ID of 4? Well, it is 4. What is the ID of 3? It is 3. And if you remember what we did in the union method, we simply scan through the array, and wherever we see the value 4, we replace it with Q's ID. And that's what you see here. You scan through the array, and when you see a 4, you replace it with a 3, okay? Q's ID. And now notice that P and Q have exactly the same component identifier. So P has the component identifier 3, 4 has the component identifier 3. So they have been put into the same component, right? And the number of components has gone down. So from 10, which is what we had to begin with, to 9, because now you have merged 4 and 3. Okay? Let's take another input, 3 and 8. Now, what is the component identifier for 3? Well, simply consult the array. It is 3. What is the component identifier of Q? It is 8. And how did the union method work? Well, it simply scans through the array, and wherever it sees this value 3, it replaces it with this value 8. So there was a 3 here which got replaced. There was a 3 here which got replaced. All right? And the number of components has now gone down to 8. Right? And now notice there are 3 sites that are part of a single component that has the identifier 8. Okay? So the site IDs 3, 4, and 8 belong to a single component whose identifier is 8. So let's look at one more input. Let's say we get 6, 5. What is the component identifier of 6? Well, it is 6. What is the component identifier of 5? It is 5. Well, how does the union method work? It simply scans through the array, and wherever it finds a 6, it replaces it with a 5. So there is a 6 which is replaced by this 5. And since a connection was made between 6 and 5, the number of components goes down from 8 to 7. Okay, so that's how the union the method works. And we keep doing this until we process all the pairs. And finally, this is the state of the ID array, right? And just by looking at it, we should be able to tell how many components we are left with, right? So how many different values do we have here? Well, we have 1 and 8, right? Which means that there are 2 components. So 0, 1, 2, 5, 6, 7 belong to one component with the identifier 1, and 3, 4, and 8, 9 belong to another component whose identifier is 8. Yep. So that was a trace of the union method. So now let's look at another implementation of the Union Find API. And this implementation is called the Quick Union UF implementation. And let's see how this works. So here, for instance variables, again we have an array of primitive integers, it's called parent, and then we have a count which simply keeps track of the number of components, right? Now parent is similar to the ID array from our previous implementation. So parent looks like this. Parent, it's a one-dimensional array of size n. Okay, but the interpretation is very different from what it was in the previous implementation. All right. So here, the values that we're going to have for each site is going to denote the ID of the parent of that site. All right. So that's how you want to interpret the values here. So you can think of each component here as being a tree, and what we are what we store as values here is simply the ID of the parent of a particular site. All right, in that tree, and we'll see how this works. Okay, so those are the instance variables. Now let's look at the constructor. So here we first create the parent array as an array of n primitive n's, and then we simply initialize count to n. So this is similar to what we did in the previous implementation. So we're saying that initially the number of components is simply n. Every site is a component. And when the parent array is created in this manner, every element is initialized to 0, or 0 to begin with. Right? And just like what we did in the previous implementation, we initialize this array such that 0 corresponds to 0, 1 corresponds to 1, and so on, and n minus 1 corresponds to n minus 1. Okay? So here what we're saying is that when no input has been processed, the parent of a site is the site itself. Okay? So 0's parent is 0, 1's parent is 1, and the parent of the site n minus 1 is n minus 1. Right? So every site is its own parent to begin with. So the running time here is n because of this for loop that goes from 0 all the way up to capital N. What about the find method? Well, the find method is quite interesting. So what we do is we are given a site ID, P, and we want to return the component ID of P. Okay? So what we do is, as long as P is not equal to the parent of P, we update P by saying P is the parent of P. Okay? And we stop precisely when P equals parent of P, meaning we reach a site whose which is its own parent. Meaning, if you look at a component as a tree, we have something like this. So we start here, and then we check if P is not equal to parent of P, and if that's not the case, we set P to be its parent. So now P is that, and then from here we again check if P is not equal to parent of P. Well, the parent of P is this guy, which is different from this, so we update P to be that, and when we get to the root of this tree, we're going to have a scenario where P is its own parent, right? So that's when we stop and we return the ID of this root of the tree, and that ID is also the component identifier. Okay, so that's what we are doing here. And notice that initially, when no input has been processed, if you ask for the parent of a particular site, you're going to get the site ID itself, because this condition is going to be false right away, and you simply return the site ID. Okay. Okay, and then we have the count method, which is extremely simple. We simply return count because that keeps track of the number of components, right? And then the connected method is also fairly straightforward once we have find in place. So what we do is we simply find the component identifier of P, and we find the component identifier of Q using this kind of a mechanism, which is what is implemented by the find method. And then we simply compare the two component identifiers. If they are the same, we return true, meaning P and Q are connected. And if they are not the same, we return false, meaning P is not connected to Q. Okay, so that's that. Okay, now what's the running time of these guys? Well, here we have to do this loop, and which in the worst case is n, right? So this is a linear algorithm. This guy here simply returns the value of an instance variable, so that's constant. And how about connected? Well, connected makes calls to find. Find, we said, has a running time of n in the worst case, because it has to traverse this list, and there are n elements. Okay? So in the worst case, it has to look at n elements. So this is also n because it relies on find, which is n. Okay, so the last method that we have to look at is the union method. So here we get two site IDs, P and Q, as arguments. So the first thing that we do is we get the component ID of P, which we call root P, and we do that by simply making a call to the find method. Okay, and then we do the same thing for the component ID of Q. So that's called root Q. And if both are the same, then it means that P and Q are connected. They belong to the same component. So in that case, we simply return. There is nothing to do. Otherwise, what we do is we say the parent of root of P is simply root of Q. All right? So by doing this, we are associating P and Q to the same tree. All right? So we are saying now the tree that is rooted at P now belongs to the tree that is rooted at Q. All right? So that's what this line does. And since, so if we are here, we are actually connecting P and Q, so that reduces the number of components by 1. So we say count minus minus. Right? So that's the union method. And notice that in the union method, all that we do is this assignment when we are connecting P and Q. All right? So the union method is quite efficient in the average case. All right? So the union method makes calls to find, but if these trees are shallow, meaning if you're not looking at too many elements in the array, then this method is rather efficient because there is just this assignment here. All right. So the union method is quite efficient, which is why we call this implementation the quick union implementation. Right. So the union method is quite efficient. Okay. So let me just quickly summarize this method. So all that we are doing here is finding the component identifiers of P and Q, and if they are the same, we don't do anything. But if they are not the same, what we are doing is we are making the site P belong to the tree that Q belongs to. Okay, in other words, we are putting them in the same component, and we decrement the number of components by 1. So that's the quick union implementation. Let's now look at a trace of calls to the union method from the quick union implementation of the UF API. So here what we are looking at is the parent array. Okay. And initially, this is how it's initialized. The parent of 0 is 0, parent of 1 is 1, 2 is 2, and so on, all the way up to 9. The parent of 9 is 9. And then we get a pair such as 4, 3. All right? And what did we do in the union method? We first find the component ID or the root of P, which is simply 4, and we find the root of Q, which is 3. Now they are not the same, So what we do is we try to establish a connection. But if you remember the code, what did we say there? We said parent of root of p equals root of q. Okay, so so the new parent of 4 now is whatever the parent of q was, which is 3, and that's what is reflected in this array. Okay, now notice that the parent of 3 is 3 and the parent of 4 is also 3. Okay, and the way to visually think about this is as follows. So 4 now belongs to this tree. So 4's parent is 3, which is what is indicated by these values. 4's parent is 3 and 3's parent is 3 itself, because it's the root of this tree, and that's what is shown here. 3's parent is 3. Okay, so this is how you want to think about the array visually. Okay? Let's process another pair, 3, 8. So what is the parent of 3? Well, it's 3. Right? And what is the parent of 8? It is 8. And now what does the code do? Well, since 3 and 8 have different parents, the code, what it says is, it says parent of 3 is basically the parent of 8. Okay, so the tree that was rooted at 3 now is made part of the tree that is rooted at 8. Okay, so the parent of 3 now is the parent of 8, which is 8. Okay, and visually this is how it looks like. The parent of 8 was 8, and now 3, which is part of this tree, is made part of this tree here. Okay, and now let's check what's the parent of 4. Well, it's 3, and that's exactly what's reflected in the array. Parent of 4 is 3. Who's the parent of 3? Well, now it is parent of 3 is 8, and that's what we have here. And who's the parent of 8? Well, 8 is the root, so its parent is itself, and that's also reflected in the array. Okay, let's take one more example. 6, 5. Who's the parent of 6? Well, it is 6. Who's the parent of 5? It's 5, and we say that the new parent of 6 is whoever the parent of 5 is, which is 5, right? And that's what we see here. So the parent of 5 is 5 and the parent of 6 is also 5. And the way to think about it visually is as such. So these two guys, 5 and 6, belong to different trees, but now 6 has 5 as the parent. Okay, 6 has 5 as the parent and 5 is its own parent. Okay, so that's how we process these pairs here and update the parent array. And once all the pairs are processed, we are left with this array for parent. Okay. Sorry, that's not the final state. The final state, once all the pairs are processed, is this. Okay, and what we have, and if you think about these values visually, what we have are two trees. All right, one tree that is rooted at 1 and the other tree that is rooted at 8. Okay, and for any node inside of a component, we can find its parent just by looking at the values in the array. So what is so who's the parent of 6? Well, simply consult the array. So at 6 we have 5 here. Okay, and that's what we see here. 5 is the parent of 6. Who's the parent of 5? Well, go to the index 5, and what you see is 0, and that's what we have here. 0 is the parent of 5. Who's the parent of 0? Well, it is 1, which is what you see here. And who's the parent of 1? Well, it's 1 again. So 1 being the root of this component, it is its own parent. Okay, so all the nodes in this particular component, you can get its parent simply by consulting for each node in that component. We can get its parent ID by looking at the array. All right. And similarly, there is this component, and here again we can get for any given node we can get its parent by looking at the corresponding value in the array. And the component is rooted at 8, and 8 is its own parent. Right? Now, before we move on, so what is the component identifier of this particular component? Well, for any node in this component, find of that node is simply going to return 1. So that's how find works. Okay. And for any particular node in this component, find is going to return 8. So the component identifier of this component is 8, the root of this tree, and the component identifier of this guy here is 1, the root of that tree, right? And you should see, and you should check out why that is just by consulting the find method, right? So find method, given a site ID, simply traverses up or moves along this array until it finds a site which is its own parent. Okay? So for this component it's going to stop at 1, and for this component it's going to stop at 8. Okay. All right, so that's a trace of calls to the union method. And now the last implementation that we're going to consider is the weighted quick union UF, and this is just a slight variant of the previous implementation. All right. So let's go through this. Here are the instance variables for this implementation. We have the parent array, which is exactly what we had in the previous implementation, and then we also have the count variable that keeps track of the number of components. In addition, we also have this array called size, which is an array of primitive ints. Okay, and what size is going to store is simply the size of each component. All right. So initially, when no input is processed, every site is its own component. So the size is going to have 1 initially for each element, which means that initially the size of each component is 1, and then it's going to be updated as the inputs are processed. And at the end, it's simply going to reflect the size of a particular component to which a site belongs. Okay. All right. So let's now go through the constructor. So in the constructor, we create the two arrays, parent and size, each of size capital N, and then we say to begin with the number of components is simply the number of sites. Right? This is what we did before. And then we initialize the two arrays, parent and size. For parent, we do exactly what we did in the previous implementation. We say parent of I equals I. So parent is an array all the way up to n-1, and size is also an array that goes 0, 1, and so on, all the way up to n-1. Now parent of 0 is 0, parent of 1 is 1, so on, parent of n-1 is n-1. So that's what we do here. And then we say size of I is 1. So for each value here is simply going to have 1. And what does that mean? It's exactly what I said before. To begin with, when you have not processed any input pairs, every site is its own component. Okay, and what's the size of each component? Well, it's exactly 1, right? So that's what we have here. Okay, so that's the constructor, and the running time here is clearly n because of this loop that goes from 0 all the way up to n. Now let's look at the find method. The find method is identical to what we had before. Okay, so what we do is, given a site ID, we simply traverse up the tree to which that site belongs until we find a site which is its own parent. Okay, that's when the while loop stops and we return that ID. All right. So we're simply returning the ID of the root of the tree to which this site belongs. Exactly the same implementation as the previous one. The running time here is n. What about the count method? Again, exactly the same. It simply returns count and the running time is 1. What about connected? Again, identical. Just make calls to find with this site ID and this site ID, and if they match we return true, and if they don't match we return false. And here the running time again is n because we make calls to find. What about the union method? Well, the union method is almost identical to the previous implementation with a small twist, and a small but important twist. So we get the root of the tree to which P belongs to by a call to find. We get the root of Q, the tree to which Q belongs to, again by a call to find. This is what we did before. Okay, so this is basically the identifier, the component identifier of P, component identifier of Q. If they are the same, there is nothing to do, we return. Otherwise, what we do is something very different from the previous implementation. We check the size of the tree to which P belongs. Okay, and if it is smaller than the size of the tree to which Q belongs, okay, what we do is we say the parent of P is root Q. So what we are doing is we are making the smaller tree be part of the bigger tree. Okay, and the reason for doing this is so that the trees that you end up with at the end are shallow. Okay, and because that's going to help the find method, because find is going to do better on trees that are shallow because it won't have to do too many iterations here. Okay, so we always try to keep the trees shallow, and the way we do that is by associating the smaller tree to the bigger one. Okay, so if P's tree is smaller than Q's tree, we associate it to the Q's tree. And then we say, and since we have made P's tree be part of Q's tree, we update the size of Q's tree by incrementing it with the size of P's tree, because all of P's elements have become part of the component to which Q belongs to. But what if the size of P's tree is not less than Q's tree? Well, in that case, we do the opposite. We make Q's tree be part of P's tree, because here P's tree is the bigger one. Okay, and in that case, we say that now the tree to which P belongs to has these many more elements, the ones that were part of Q's tree. Okay, so that's the idea. We always associate the smaller tree to the bigger one. And since we are connecting P and Q, again we decrement the number of components by 1. Okay. All right. Now here, what is the running time? Well, here the running time is going to be in the order of log of n. Okay, it's because of the way we implement things. Because we always associate a smaller tree to a bigger one, we are going to end up with these trees that are fairly shallow, which have a height of at most log of n. Okay, so here the union operation is very efficient. It's logarithmic as opposed to linear, which is what we had in the previous implementation. So now let's look at a trace of calls to union. It's what we had before. We show the parent array here. So initially all these guys are initialized to the site IDs. That's what you see. And then you receive a pair such as 4, 3. All right? So the parent of 3 is 3, the parent of 4 is 4. So what we do in the code is we make 3's parent to be whatever 4's parent was, and visually you can think of it as such. And it's this because how did we implement the union method? We check the size of the trees to which 4 and 3 belong to. Well, they are 1 to begin with, right? So this tree has size 1, this tree has size 1, and in that case, if you go back to the code, you can check that this is what you do. Okay. You make P's parent be what was Q's parent. Okay. Let's take another example. The input is 3, 8. So who's 3's parent? Well, it's 4 from the array, and you can also see that here 3's parent is 4. And who's 8's parent? Well, it's 8, right? So you can check that from the array. And what is the size of now the tree that 3 belongs to and the tree that 8 belongs to? Well, 3 belongs to a tree that has 2 elements. It has a size of 2. And 8 belongs to a tree that just has 1 element. Okay, so what does the code say? You associate the smaller tree with the bigger one. All right, so you say 8 now is part of the tree that is 3, 4. All right. So that's how this input is processed. Okay, and that's how things proceed here. You always associate the smaller tree to the bigger one, and at the end, once all the inputs are processed, you have this for the parent array, and you have this representation as trees. Okay, and here again, within a component, if you want to find the component identifier of a node, you can simply consult the array. So you start at the node and you traverse upwards until you get to the root, which has it as its own parent. Okay. So the component identifier of this tree is going to be 4. The component identifier of this one is going to be 6. Right? Now, what you should do is compare these trees with what we got in the for the previous implementation. And you will see, even with the small example, that the trees here are shallower than what we had in the previous implementation. All right, and as a result, the find operation is fairly efficient. So is the union operation. Okay, so the weighted quick union implementation is much more efficient than the quick union implementation. Right? And certainly much more efficient than the quick find implementation. Now, before we proceed, there is one point that I want to make where the quick union implementation is problematic. So, for example, if the inputs arrive in a particular order and in a sort of like a pathological order, such as 0, 1, 1, 2, 2, 3, 3, 4, and so on. With the quick union implementation, what happens is this results in a tree that is basically like a linear structure. Because when you get a pair like 0 and 1, what you do is you have something like this. So you have 1 whose child is 0. Okay, and then you get the pair 1, 2. So the way quick union works is it will set 1 be the child of 2, and then when it gets to 2, 3, it will make 2 be the child of 3, and then when it gets to 3, 4, it will make 3 be the child of 4. So as you can see, when inputs arrive in this pathological order, quick union results in a tree that is linear, and it's a very tall tree, and as a result, find suffers, because when you make a call to find the component identifier of a node, you have to traverse a list that has order n. Okay. Now, with the weighted quick implementation, we don't have this problem. So even when the input is pathological, such as this, you don't get tall trees, but you get very shallow trees. Okay, so So the weighted quick union implementation is extremely robust. It results in trees that are shallow, and as a result, the calls to find and union are extremely efficient. Okay, so the calls to find, in the worst case, they only have to traverse trees that have order log of n. All right. Okay, so we are done with the different implementations of the Union Find API. So all that we need to do is discuss their performance characteristics, and that's what is shown here. So in this table, we see the different implementations listed here, and then we have the cost of the constructor, the running time of the union method, and the running time of the find method. So with all the implementations, it's clear that the constructor takes linear time because you have to set up those arrays. Okay? And those arrays are of size capital N. What about the union method in quick find? Well, there we had to traverse that array called ID, okay, which had a size n, so the union operation is linear. Whereas the find operation just involved array access, so that was constant. In the quick union implementation, union was tree height. And we say tree height because in the worst case, where the inputs arrive in a pathological order, you might be traversing a tree that has size n. All right? So union has tree height as the running time. Similarly, even the find operation has the tree height as the running time, which in the worst case might be n when the inputs arrive in a particular order. Right? The weighted quick union is fairly efficient. So there we end up, as I said before, with trees that have heights at most log of n. So the union method has cost that is log of n in the worst case. Right? And the find method also has cost that is log of n in the worst case. Okay, because the find method has to traverse these very shallow trees which have height at most log n. And there is another variation of the weighted quick union implementation that we have not talked about here, but it's discussed in our text, and that involves this idea of path compression. And if you do that, the union and find method is even better than what we have for the standard weighted quick union implementation. So it's close to constant time in the amortized sense. Okay, and it's worthwhile looking into that implementation and see how that's done. So you can get the costs of union and find down to constant in the amortized sense. But what is not possible is make it absolutely constant. Okay, so that's simply not possible. So the best that you can do with the union and the find operations is making them constant time in the amortized sense, which is what is done by this implementation of the weighted quick union with path compression. All right. Okay, so that concludes this section on the union find data structure. Thanks for watching.